Hey y'all, welcome back to Alakazam Math Made Easy. In this video, we're going to go over a topic we've kind of already introduced briefly, and maybe you practice it. I included it in a video from the first derivative section, just in case your professors put it on the first exam, but typically this concept falls under the second exam because it's an application of derivatives and higher derivatives. So just a couple things to review before we jump into the new stuff. Remember to find where the function is increasing or decreasing. You find the derivative itself, set it equal to 0, and then solve for x. And then from there, you draw a number line, and then test the ranges of values on different sections of that number line by plugging values into the first derivative. So for increasing and decreasing, you use the first derivative. That's super important. And then you interpret the results, right? So if I plug the value into the first derivative and get a positive value, that means the function is increasing in that range. If I plug it in and get a negative value, that means the function is decreasing. So that should be pretty much review. So should this, right? At this point, concavity should be something you're pretty familiar with as well. So concavity is basically the same process, but with the second derivative, right? So find the second derivative of the function, set it equal to 0, solve for x. Those will be your inflection points, the points where it changes from concave up to down or down to up. And then you set a number line with the x values that you just found, those inflection points, on the number line. And then you test all of the ranges outside and in between those x values by plugging them into the second derivative. So remember, for increasing and decreasing, we plug into the first derivative. And for concavity, we plug into the second derivative. And then again, it's just an interpretation, right? So when I plug my x value in, the one that I'm testing, and I get a positive number, that means that in that range, the function is concave up. And if I get a negative number from testing that, it means it's concave down. So in this, in the last video, we talked about this. We kind of went through we rushed through a pretty vague example where there were approximations and not 100% exact. So what we're going to do is we're going to go through another video on how to or another example on how to combine all of these components into an approximation of a function that might be otherwise difficult um, to graph, right? So first we'll go over the general steps just as a reminder. So the first step is obviously find the critical value. So first derivative equals 0, solve for x. And then second step is to build your number line and evaluate where the function is increasing or decreasing, right? So basically this piece here is the increasing, decreasing section. And then steps 3 and 4 are the concavity section, right? So second derivative equals 0. And then what we're going to do from there is build our number line again and evaluate using the steps we used above, the concavity of the function. So the question becomes, why do I need both of these, right? If I have increasing and decreasing, why can't I build a function just based on that? Why do I need concavity as well, right? And that goes into what kind of is shown in these models, right? Why do I need both? Well, because both of these functions are increasing, but one of them, this one here, is concave up, and this one is concave down. So even though they're both increasing, the shape of that graph is very different, right? So that's why just having one of those values isn't enough. You need both of them. So once you found the ranges where your function is increasing and decreasing, you take all of the x values that you found when you set the functions equal to 0, and you find what those y components are, the y value at that x from the original function, right? So because we want to graph something, right, we need a coordinate, we need an x and a y. And what we're going to do is we're going to take advantage of the fact that we know that these x's are important on our graph. We know that something cool will happen at those x values. So we're going to take advantage of the fact that we have a list of x's and we can find a corresponding list of y's. And because, remember, this is the part where people get a little bit confused. So remember, for this step, we're going to plug into the first derivative. And then For inflection points, we're going to plug in to the second derivative. And then for the actual function values, we're going to use the original function. So that's super important because if you plug into the other functions, you should get 0. So like if I plug in a value that I got from step 1 into the derivative again, I should get 0. Same thing with step 3. If I plug in a value I found at step 3 into the second derivative, I'll get 0. So definitely make sure that when you find the y values of each point, you're plugging it into the original function. And then the last 2 steps are to plot the x and y coordinates you found in step 5, and then use the stuff that you found, use these ranges that you found in step 2 where it was increasing and decreasing, and in step 4 where it was concave up and down, use those to connect the dots that you plotted in step 6. So that's a lot of steps, but basically what I was doing is I was trying to put it in one consolidated place so that you guys could like screenshot it or whatever you want to do and make that part of your study guide, right? But let's go through an example. So the function we're going to draw a graph for is f of x equals x cubed minus 2x squared. And I don't think anyone off the top of their head can produce a graph for that that looks relatively accurate without going through some steps. That's not 100% an easy like translation scaling kind of function, right? So this first step, remember the first step is to set the first derivative equal to 0 and solve for x. So that's what we do here. We get x equals 0 and x equals 4/3. And remember the second step is to then use the process to find where the function is increasing and decreasing. So then we have the number line and then we interpret the result of that. So the actual x values I solved for were 0 and 4/3. Oh, wow. That's weird. Were 0 and 4/3. But I have to pick numbers between those, right? So I have to pick a number less than the smaller one, greater than the higher one, and highest one, and in every range in between, right? So that's where I picked these numbers from. It doesn't matter which numbers you pick. So generally pick numbers that are easy to plug in, right? Which is usually 1, 0, and then -1. And then after that, just whatever number you think would be easiest. And then you plug it into the first derivative, right? And that's how I got the results in step 2. I found that it was increasing to the left of 0 and to the right of 4/3, and then it was decreasing in between. So that's awesome. And then the next step is to find the second derivative, right? And what we're going to do there is we're going to follow the same steps, set it equal to 0, solve for x, use the number line, get the ranges, right? So that's what we ended up doing. And the ranges we got were that it was concave up between or everywhere higher than x equals 2/3, and it was concave down everywhere to the left of x equals 2/3. So now what we want to do is we want to plug in the values we got, right? And test them. So remember, we got 0 and 4/3. We got 2/3. So those are the 3 values we're going to test. And you'll see that's exactly what I did here. I did 0, 2/3, 4/3. So again, what we're going to do is make sure that we're plugging these into the original function, which was x squared minus, or x cubed minus 2x squared. So you'll see that that's exactly what I'm doing. And then for reference later on, obviously this equals 0. I approximated this to be, because I ended up drawing my axes in terms of thirds, right? So that works out to be a little bit less than, or I guess technically more than negative, let's see, 2/3. It's a little bit less than that. But it's a rough enough approximation. And then this one we ended up saying was a little bit less than 4/3, right around 4/3. So that's what we ended up approximating. So what we're gonna do is combine everything, right? So this next step is to plot the coordinates. So that's what I did with those blue dots, right? And I'm actually gonna delete this so we can go through this process together. But those blue and yellow dots here are my coordinates. So what else do I know? I know that from 2/3 and up, this thing is concave up, so it should be kind of in like a bowl, almost kind of form, bowl or cup, right? And then everywhere to the left of 2/3, it'll be concave down. So that's helpful. I also know that everywhere to the left of 0 and to the right of 4/3, this function is increasing, so the slope should be positive. And then everywhere in between that, obviously, it's decreasing. So that's what I know. So how do we turn that into a graph, right? Putting all these pieces together. So we have our points. And okay, so I would recommend starting with concavity, right? So this chunk, this graph is essentially picked up into 2 parts. And we know that from here, generally, this section has to be concave down. And actually, by drawing it like that, that actually was a pretty good representation, because we also know that in that section here that's concave down, we know that it has to be increasing from here to the left and decreasing from here to the right. So that was actually a pretty good model of what we wanted to look for. So this section here is clearly increasing because the slope is going up as x goes up. And then maintaining that same general shape, but now making the function decrease, that's what it would look like for the decreasing half of that function, right? So it's still, this whole section here is still concave down, right? It's like a frown overall, the whole range, but it's increasing at the beginning and then decreasing at the end. So that's what we needed. Now the same logic follows in this other half right here. So concavity is up at this point for everything left or to the right of 2/3, and this left half here is decreasing and this right half is increasing. So how do we put that together? We follow the same logic we did before. So concave up, oops. So concave up means that it should now look like a cup. So we have that, and then that's decreasing, right? Because the y values are getting smaller as x values get bigger. And then for the rest of this section, we keep that same general shape and then make the slope increase. So that's the logic on how to actually construct a graph given just the function, right? You can do it by plug and chug, which is super annoying because to get these values, you're gonna have to, or to get a shape this good, you're gonna have to plug in some sort of, like you're gonna have to plug in a bunch of numbers, right? Whereas opposed to this, we built this graph with just 3 points. So that's super helpful, because if I didn't know that this was a cubic function and I didn't know that the ranges were increasing and decreasing at these points, I could connect them like this. I could connect them like, because if I didn't know these were maxes, mins, and inflection points, I could connect them like this. Oops, I have to actually hit them to connect them. So you can tell right away that because we used the first and second derivative, using 3 points made our function more accurate than it would have been having just an approximation using 3 points. So if you learned something from this video, give it a like. If you want to stay up to date when I add new videos to this channel, subscribe and turn on your notifications. And if you have any questions, as always, you can leave them in the comments and I'll answer them as soon as I can. And best of luck.